button on the Go to Webinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast. The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone. I'm just seeing if you can hear me properly. Can someone just write me a little note? Can someone just ping on the screen if you can hear me properly? Alrighty. I'm gonna wait for 30 more seconds before I start. You can see my screen too, right? Alright, cool. Let's get started. Hello everyone, I'm Devendra. I work for DataTorrent. I've been a data architect for quite some time now, working on big data systems. And I've been working on Apache Apex in its current form and in the enterprise editions for quite a while now. Let's take a deep dive into what Apex is first. It's a platform and a runtime engine that enables development of scalable, fault-tolerant applications. It's Hadoop native. What it essentially means is that it leverages a lot of underlying Hadoop components for fault tolerance, scale out, multi-tenancy, etc. It's Yarn native in the true sense of the term. It uses Yarn underlying Yarn features around multi-tenancy and scheduling, um, data locality, etc. out of the box. It's a unified engine for both batch as well as streaming. The philosophy that Apex takes towards data processing is that stream is a superset of batch. This is for the other systems, like for example, Spark Streaming recently came out with the philosophy that a stream is unbounded batch. Systems like Apex, Flink, etc., work on the philosophy that stream is a superset of batch. And if you have a truly streaming engine, you can do batch processing with it as well. It's a high throughput, low latency architecture based on windowing and checkpointing for statefulness. There are a bunch of library operators available out of the box uh, for commonly seen use cases, and the application user really needs to take care of writing his or her business logic while assembling an application and running a distributed system on top of Apex. I'm going to quickly take questions if there are any on the how to write notes. How to write notes. I didn't understand this question. I'm sorry. Can custom business logic be written in Scala in operator? Yes, it can be. I believe even scripting is supported with Python and a few others. So yeah, that can be done. Plus, there is a Scala API as well to write Apex code, so you can leverage that too. Applications on Apex, yeah. So some of the salient features of Apex revolve around distributed processing. Which basically means that you can break your application logic into these logical parts we like to call operators, which run a specific code of your operation of your distributed system. Um, uh, then you can assemble these operators together into forming an end-to-end architecture. I'll come to it in a little bit in more detail. Operators, which are singleton pieces of code running, logical code running, can be scaled up and down in real time at runtime based on some load factors or SLAs. Apex gives you strong fault tolerance guarantees. Apex can automatically recover from node outages. Apex applications can recover from node outages, and they don't have to start from the beginning. Apex utilizes an incremental checkpointing mechanism. So the most you would reset is till the last checkpoint. Typically, checkpoints occur every 30 seconds, so it's not a large recovery state. Apex takes care of statefulness using checkpoints, like I mentioned earlier. Checkpoints are incremental, which basically means that after a window is committed across the DAG, your previous checkpoints are purged because you don't need them anymore, and so on. It's ideal for longer running scale out applications because there would be a lot of state. Apex gives you a Malhar library of operators, which cover the more prominent operators. Fault tolerance is built into them. Most of them are enterprise ready already. Apex gives you a Java-based API primarily, but there is a Scala-based one too. The Java-based API is what you call a compositional API. Compositional APIs are typically lower level APIs that give you more granular control of how you want to process something. A declarative API is something that is used in the Spark world, where you say read from somewhere dot filter dot map dot reduce by key. So that is a declarative API. It's more higher level, gives you lesser control over things in that basically use custom logic. But with Apex, that's a relatively easier problem to solve. Um, on top of this, DataTorrent RTS gives you operational insights for how your distributed application is running on the cluster, and also gives you a bunch of other insights on application assembly, and thereabouts. Gonna see if I have questions. Okay, none right now. Gonna move on. Here's an overview of the stack. So Apex is compatible with any physical or virtual clouds, and also with on-prem and off-prem deployments. So you can run it on a physical machine, on a virtual machine that can be in AWS, Azure, Google Data Cloud, or on-premise with any of the major distros supported. The only prerequisite Apex has is Hadoop 2.x, because it's a Yarn native application. It leverages Yarn for both resource negotiation and scheduling, and Heartbeat protocols for monitoring. So the only thing it needs is Hadoop and Yarn, nothing else. It's certified against all major distros: Cloudera, Hortonworks, Pivotal, Malhar, and is compatible of running with all of them. Even Azure flavors run very well with it. HD Insights. On top of this, you would have the streaming runtime, or the Apex core engine. It's a high-performance, fault-tolerant, in-memory data processing engine. Apex is based on the philosophy of taking data to compute and not compute to data. Taking data to compute works very well with scale-out architectures, the ones that run on thousands of nodes doing a lot of heavy processing. Compute to data is based on the notion of exploiting the data locality principle of Hadoop. Typically, with smaller clusters, that can work well. Spark uses that principle. Spark Streaming uses that principle because it's an inherently batch engine. So the DAX scheduler can theoretically keep on scheduling the compute on the same node where that data is residing. But that doesn't work well with larger deployments, wherein data is only residing on a few nodes and you're doing a lot of compute. Then you would be scheduling tasks on the same node all the time, and DAX, the size of queue inside the DAX scheduler keeps on increasing because a lot of tasks are not going to be scheduled. Again, that has an implication on the latencies per se. On top of the streaming runtime, you would have the Malhar open source operators, which are compatible with the streaming runtime, and you would assemble you would pull in Malhar open source operators to assemble your streaming application running at this layer. On top of these, DataTorrent gives your RTS Enterprise Edition, which focuses on making things in terms of application development and operations easier. So there is a graphical application design and launch console, which lets you build a DAG, just drag and drop operators and assemble them and launch them. It gives you solutions for visualizing in-stream data. And in addition to that, there is a management console for operational use. There's a REST API that interacts with the streaming runtime to change, let's say, the flow of DAG, or some properties on operators on the fly can be done with the REST API. REST API also gives you a way to have more insights into your streaming application by capturing some metrics and measures on operational side of scheme of things. Quickly going to take a question. Can Apex work as Solr? I believe there is a connector for Solr with Apex. Yes, it can work is my answer for that. Yes. Yeah. Okay. Apex, so Malhar basically takes in operators that are more commonly used, or some specific ones are also available for, let's say, NiFi integrations or Solr integrations and stuff like that. But a lot of them are enterprise ready, especially around the file system operators, both in and out are enterprise ready. They do idempotency exactly one semantics. Kafka one is production grade. Again, idempotent exactly once. There's one coming up in the RDBMS space, which is closer to, it does exactly once reads two. On the NoSQL side, there are operators for Hive and HBase, and I believe MemSQL too. On the messaging side, most of the JMS backed ones are supported. Um, and and on the compute side, there is a tight integration with Samoa, which is a machine learning library. And there are stat and math operators for usual statistical functions, mean, mode, variance, regression, etc. And pattern matching, most of pattern matching algorithms are supported as well. Okay, gonna take a question quickly. Okay, all right, no questions. All right. Here's how your Apex application would look on a cluster. So this is a logical view of the cluster, right? So there are 4 data nodes, 1, 2, 3, and 4. There's a resource manager and a per node manager. So Yarn is the resource manager. Apex command line interface interacts with Yarn to submit applications. Here we have shown the green boxes are your Apex operators or Yarn containers. So you can see that there is one container on the first node, 2 on the second one, 2 on the third one, and then there are 2 on the fourth one, but they're really running as a single container. So this is done to show node locality and container locality. Along with this, if you look at it, we've shown that MapReduce and Apex can run together because Hadoop is multi-tenant by itself. Now the data here is flowing from operator 1 to operator 3, operator 2 to 3, and then 3 is giving some feedback to 5 and also sending some data from 4 through 6. That's your typical application flow. In addition to all of this, there's a DT gateway and DT console that comes with the RTS editions to give you more operational insights into the way you're running your cluster. There is a streaming application master, which is one per application. So Yarn has a notion of node managers, which basically take care of all the monitoring aspects for the node. And then the streaming application master, which is per application, basically takes care of negotiating resources with the resource manager for its own application. Now, Stram in this case would negotiate resources for operators 1 through 6 with Yarn, and then they would be spawned on different nodes depending on the locality. Let's take a look at the application development model. So in this particular case, data is flowing from left to right. For nomenclature, I'll call operators more towards the left as the upstream operators, and operators on the right as the downstream operators. For example, this is an upstream operator, this is a downstream operator, so on and so forth. Now think of DAG is just a graph. So the nodes on this graph, or the vertices on this graph, are your operators, which basically run a logical code that you want to do your processing based off on. And the edges would be a stream of tuples. A stream is just a sequence of tuples. An operator can have one or more input ports, or the places from which you would get in your data into the operator, then do some processing, and it could have one or more output ports to basically emit data to the next operator. So a tuple a stream goes into the operator, that's a sequence of tuples going into the operator. The operator does some process. The operator receives that stream on the input port. does some processing on it, and emits that stream out of the output port. Then the next operator downstream can receive it. This model is called directed acyclic graph model. Now let's take a look at windowing support in Apex. Apex primarily supports two types of windows: sliding window and tumbling window. Um Sliding windows have a duration and a length. So you could have length 5 and slide by 1. So it's an incremental slide of 1, but length of doing that window operation is 5. And tumbling window is more like, okay, it's a fixed length window. So it would run for 3 windows, and then the next one would be triggered after 3 windows, and you would be doing some window operation for that duration. In this particular diagram, stream is represented by these white tuples. So this is your actual data flowing in through different operators. And then the platform inserts this notion of begin window and end window, which basically mark the start and end of a window. Typical duration is like 500 milliseconds. And all the processing of tuples happens within that window, but they can be emitted before the end window. There's no artificial latency that is being added there. Begin windows and end windows are inserted by the platform for checkpointing purposes. So, uh, for example, I'm doing a checkpoint every 30 windows. Then I would have 30 begin window tuples and 30 end window tuples, and all the processing would happen within the context of them. But at checkpoint, I will checkpoint the state of every operator through the DAG to a persistent storage HDFS. So checkpoints are written primarily to the local file system first, and from that point on, they are copied asynchronously to HDFS. If there is any failure, then the platform basically resets itself at the most nearest checkpoint, and then reapplies all the tuples that are stored in buffer server to that checkpointed value, so you don't lose any state at any given point in time. Let's see how an application looks like in Apex. Here there are 4 operators, so it's a basic use case, taking some input from files, emitting individual lines, parsing them, emitting words out of them, counting them, and writing the output to a console. This is your hello world of big data space, also called as word count. If you take a look here, you have 4 operators: the input operator, the parser, a counter, and a console operator. Let's just take a deeper dive into how an application looks. So all you have to do while you write your application is implement the streaming application interface. It'll give you a populate DAG method, which is to populate the directed acyclic graph with operators and streams. So here we have 4 operators: the line reader, parser, a unique counter, and a console output operator. And then you connect the operator using streams. The points of connection are ports. So line reader's output port connects to the parser's input port. So line reader's output goes to parser's input. Parser's output, or here output port, goes to counter's input port. I'm just calling that input port data in this case. And then counter's output goes to the console's input, which is counter's count port. You can name the ports to whatever you're comfortable with, just variable names that are connected, and then data will flow from input through the console. Is there a way to debug the input stream coming into the operator? Say I'm trying to understand even delays. How would I be able to see what the node is currently processing? Yes, you can do that. You can actually add, you can on the fly change the way your logging levels are, and also through RTS you get a way to query in stream events and visualize in stream events. So you can actually go to the container and visualize those events as they are flowing through your application. Okay, let's take a look at partitioning and unification. Typically, a distributed application would be running with one or more instances of the logical blocks that we call operators. So partitioning becomes critical, and once you partition the data, you have to unify it at some point to basically give a unified or a singular view of that data to external entities, right? So both of these are pretty important concepts. Let's take a quick look at it. Your logical application or DAG would look something like this: three operators, operators 0, 1, and 2. Uh, they are they're just shown as single instances here, but that's not the case. When you assemble an application, this is how it looks like. When you run it on a cluster, it could look a lot different, right? Because you may want multiple instances of the same operator. So here's a physical diagram of operator 1 with three partitions. So operator 0 has one partition, operator 1 has three partitions. Then the platform inserts a unifier to give a unified view to operator 2 of all the tuples coming in from operator 1. So operator 2 has one partition. Here's another example of n cross m partitionings. So partitioning can be of two types: n cross m, where upstream operators have n partitions and downstream have m partitions. And then the other scheme is parallel partitioning, where the number of upstream and downstream operators is exactly the same. Um, Here's an example of a logical DAG. So you have operators 0 through 3 coming in, and then operator 1 has three partitions, operator 2 has two partitions, and operator 3 has one partition. The platform inserts unifiers to combine data from three upstream partitions of operator 1 so that two downstream partitions of operator 2 can consume them, and then there's another unifier that goes from 2 to 3. Here we have shown that unifier 2 could become a bottleneck, so the platform can actually split the unifiers so that only a subset of data from 1A, 1B, 1C goes through one unifier, and the other subset goes through to the other unifier. To control this, there is a notion of stream codec, which basically tells the downstream operator what part of data from the upstream it has to consume based on a mask. So this basically avoids a unifier bottleneck. Now let's take a deeper look into the other way of partitioning, which is parallel partitioning. Let's say I have a physical DAG that has only one operator partitioned into m cross n. So here operator 0 and operator 1 are partitioned using the m cross n partitioning scheme. This is resulting, this as shown in the picture is resulting in a bottleneck at the unifier, let's say. So I can tell the platform to change the partitioning scheme to a parallel partitioning scheme. So now I have 0 and 1 still in m cross n, but now I'm saying everything after operator 1 has to be in a parallel scheme. Now you will have 1a and 1b, and then 2a talking to 1a and 2b consuming from 1b, 3a consuming from 2a, so on and so forth. The other way bottlenecks can happen and how a unifier solves that problem is showcased here. Let's say the logical plan has only two operators, one upstream, one downstream. Look here. And then my physical plan basically has four upstream operators, four partitions of the upstream operator. And I think there's a question. Let me just quickly take that. Okay. All right. Okay. Anyway, so all right. Unifiers. Sorry. Here is an example where there are four upstream partitions of the operator, and then there's a network interface card over which all of that data is going to a downstream operator. Now the platform would insert unifiers, which are typically more co-located, and partition that upstream data into two unifiers. So just to reduce the chattiness over a NIC. NIC is a network interface card. Typically, NICs could be a bottleneck if a lot of shuffle is happening. Now you have instead of one unifier, you have two unifiers taking half the data from the upstream operators each, and then sending that to the unifier downstream. Typically, this works very well. Just going to take a quick question. Would the unifier handle partitioning issues where there is a data skew? Yes. So partitioning is driven by hash codes by taking a hash, applying a hash function on the hash code of the Java object that is being serialized and deserialized. And typically it's a decent skew because hash codes are by default random. And even after that, if there is a data skew, you can actually say that you want a round robin way of sharding data across your downstream operators. and then unifiers would be inserted in a cascading way through that to handle that load. Let's take a look at dynamic partitioning. Dynamic partitioning is the ability of an operator to scale up and down depending on the input load. So basically, partitioning changes while an application is still running. While this may sound really nice and exciting, in reality, what you have to do is maintaining state is critical when this happens. So Apex takes care of that out of the box for you. There isn't a lot of code that you would have to write for it. Dynamic partitioning is typically based off on some SLA or some threshold or a velocity criteria. For example, the Kafka input operators that come with Apex are capable of dynamic partitioning out of the box based on the input velocity of events. When you split partitions or you increase the number of partitions, you have to redistribute state. For example, with the Kafka operators, you go on from 2 partitions to 4 partitions. Now, the new 2 partitions have to know which offsets they have to start reading from. Otherwise, they will be essentially stateless and start consuming either from the start or from the end. So that's state maintenance, and that's taken care of by a lot of Apex operators and the platform also. There is a partitioner API that's available with Apex to basically write a custom partitioner if you need to. It's available out of the box again. Here I'm not showing any unifiers because they'll just clutter the diagram. Now let's take a look at a typical use case. I'm going to pause for like 30 seconds before moving on. Now we are diving into the customer use case that we have. Feel free to write any questions. Happy to take them at this point. Actually, I'm just going to rewind to dynamic partitioning, and in the interest of users, just cover a little bit on it on like vis-a-vis Spark streaming. So Spark streaming recently introduced a notion of dynamic partitioning as well. But the way that dynamic partitioning works is based off an exponential scale up and down algorithm. Basically means that if you have 2 partitions of like a Kafka receiver today, then and the SLA is not met or the velocity of events is too high, then you would scale up to 4 partitions, then to 8, 16, 32, so on and so forth. So it increases in powers of 2. Now, how is state handled in this case, right? So for Spark streaming, for handling state, uses a shuffle server, which is another daemon which is another server that you have to start up while you're running the Spark application, so that all the operators write their state to that shuffle server, and all the operators read their state from that shuffle server. On a scale out architecture, this typically would end up becoming a bottleneck because everyone, all the operators in the DAG are trying to write to that shuffle server and read from it. And then the other thing is that it's not really a dynamic scale up and down, because you check periodically if the threshold has gone down or up and not continuously. And then you only reduce the number of partitions after that periodic time. So you could still be using more resources than you need to at any given point in time. So while available, dynamic partitioning is not really enabled in the true sense with Spark streaming. Ingesting, here's a use case that we saw with one of our customers, and we worked with them to achieve it. So that customer was a large tech company, advertisement technology company serving ads across the world. They were ingesting data from Kafka and S3. S3 is a simple storage service offered by Amazon, essentially an abstraction over HDFS. They were parsing data, filtering the output data of the parser, then doing some lookups based on flat files as well as databases. The flat files were changing periodically. They were giving some metadata and changing over a period of time. After the enrichment, they were doing dimensional compute, basically to compute some of the key performance indicators. And after that, they were reporting critical metrics around campaign monetization, just to see how their ad campaigns were doing in the real world, what the user response was to seeing a certain ad, if people were clicking on that ads, so on and so forth. The aggregate functions that we saw with them were typically some around, some as in additive aggregate functions, and then they were doing some top end and some sorting on critical performance indicators. Uh, in addition to this, they were using a low latency publisher subscriber model using a Kafka based pub sub. So they were actually interacting with their UI using Kafka as an intermediate message bus to talk to it for low latency querying. Quickly going to see if there are questions. No, none at the moment, I believe. Okay, I'm going to move on. So let's map that set of requirements or the use case to how it would look to an end user. This is how it looked. So you have the KPIs up top, and there's a publisher subscriber, so a request response mechanism. So this is just a sum of total impressions per ad delivery over a minutes interval, and on your right you have like a top end per advertiser, and this is how your queries would look like. The end user logs into a screen, he drops in a query saying, okay, I want my ad delivery, I want the number of impressions for my ads per minute for the last 20 minutes, and then you would drop in a query to your Kafka, and then the DataTorrent enabled or Apex enabled dimension store would listen to that query from a topic in Kafka, do a lookup in a distributed hash table, and send across the results to the UI again, and then you would see these Manhattans rising and falling. Same for the top end. Apex would store the top end results in an in-memory data grid of sorts, or an in-memory distributed hash table of sorts, and then respond with the top end values for a given advertiser in real time. Let's take a look at the scale that they had. They had 6 geographically distributed data centers. They were both on-prem and off-prem. So 3 of them were co-located within their own data centers, and the other 3 were in Amazon. This is an ad tech company, so they serve ads across the world. That's why they need more geographically located data centers closer to where their customers are. They had a total of 5 petabytes under data management, and the inflow rate that we were seeing through our real-time system was 22 terabytes a day. And these were essentially auction and client logs, ad serving logs generated after serving ads, or the logs that come from a user's browser when he or she views ad or navigates to a page and there's ad served to them. The log formats for both these types of logs were heterogeneous. One was JSON, the other was Avro. And we were crunching in more than 15 billion impressions per day. The average flow of events was 200,000 events, but at peak that would go to double of this, more like 400,000 events per second. I'm going to continue. So the initial set of requirements, so this project was staggered in phases, and the use case evolved as we went along. The initial set of requirements were more centered around consume ad server logs from files. So essentially, the files would be written in batches, and you would consume data from files. The files were uploaded to S3 every 10 to 20 minutes, and there was a chance that data could arrive out of order in S3. For example, data for 10:30 could arrive after data for 10:35. So essentially, there was some out of order processing that you had to do. So we maintained a notion of time within our aggregations to achieve that. Event size was about 2 KB when the events were decompressed. And aggregates were kept in an in-memory distributed store with a strong policy on expiration. So what happened was there was a requirement to have minute level aggregates, day level aggregates, and week level aggregates. Then you would typically keep your minute level aggregates for an hour, then you would keep your hour level aggregates for a day, and then you would keep your day level aggregates for 7 days. So this in-memory data store had to have expiration policy, so that was also built in. And then like I explained earlier, there was a front-end integration through a Kafka-based publisher-subscriber mechanism for interacting with the dashboards. Here's a look at how the architecture looked like. So they had there's a co-located data center and an Amazon-based data center. Ad servers are generating logs that are being relayed to a Kafka cluster in the co-located data center, and they are being relayed to a Kinesis, which is again a service provided by Amazon, pretty similar to Kafka. It's a streaming ingestion service. From Kafka and Kinesis, the logs were copied over to S3. From Kafka using a batch consumer, from Kinesis using a Kinesis consumer. The Kafka consumer was a component called Cameo, which is a LinkedIn open sourced Kafka consumer. From that point on, we were reading that data from S3 using a partitioning policy. Different buckets of S3 were being read in a recursive fashion, and they were also being pulled if any out of order or incremental data was arriving in those buckets. Let's say I pull it at time 1036, and some other file in the same bucket arrives at 1055. Then we had a mechanism to basically go back to that bucket and poll for any incremental files that there were. This S3 operator was completely stateful, used to keep a track of the files it has read, the offsets inside the file it has read, and was also idempotent and exactly once as a consequence of that. After reading logs from S3, you would filter them using some criteria, enrich them, and then do a dimensions compute based for the key performance indicators and write those aggregates down to a dimension store. An external user would drop in a query to the middleware, which would create a Kafka message of it and write it to a cluster. And then the dimension store would basically be listening on a topic in the cluster, look up that event in store, and basically drop a result to the query results topic from where the middleware would pick it up. While this sounds elaborate, this entire process did not even take a second for retrieving the queries from the store. Kafka is pretty scale out, and dimension store had multiple partitions. Plus, it did point-to-point lookup, so it was very, very fast, very less latent also. I'm going to see if I have any questions. None right now. Okay, so some of the challenges that we faced at that point were reading data from S3 was not as predictable as you would think it is. S3 has this notion of eventual consistency that started giving problems when the applications were longer running, and in some cases, because of eventual consistency issues, we saw that operators were failing. Over a period of time, we noticed that some files were getting corrupt, some file writes were getting corrupt into S3. So this is outside of the Apex application, but because you're trying to read a corrupt file, you have to handle it in a certain way. So we handled all of those as we went along. Then we noticed that reading one file per operator was essentially limiting, right? You ideally want to split the file into parts and read it at a block level. This problem has been solved using a block reader and a file splitter in Apex now. So that's available with the open source distribution. And what you essentially see is you can take a file, split it into blocks, then you can read those blocks, and then you can resynchronize the blocks. So the unified view of the file is presented to you in the order that it was. I'll show an example towards the end. So out of order data processing was also a problem, both on the input side as well as on the aggregate side. On the input side, you would have files coming in later than they are expected. So you had to go back, scan directories backwards than you are right now. For example, I am at hour 3 right now, and my hour 2 file arrives. Then I have to go back to hour 2 and read that file only, and not all the files in hour 2. So that's on the input side. On the other side, you have to handle out of order data if those aggregates for hour 2 come after the end of hour 3, for example. So the dimension store had like an aggregate of aggregates and a bucketing concept at hour level to handle those kind of events. Essentially, you're setting a threshold till the time you will account for delayed records, and you will put them in the appropriate buckets as you need to. There was a spike in the load when files used to arrive. So all of a sudden, your input operators are sitting idle, and then these batch jobs would write a ton of files to your input directory, and then there would be a spike in consumption, and then again there would be a period of inactivity. Now in this particular case, while you're really running a streaming system, because your input is batched, you can run a streaming system only when you receive an input. So there was some latency introduced, not within the Apex context, but from external entities. um, I think memory requirement for the in-memory store became a challenge as we went along. Cardinality estimation for incoming data became critical, because over a period of time you will have more and more unique combinations, and you have to store them separately in the store. I mean, in a partitioned way in the store. I'm just going to see if there are any more questions. None. Okay. Here's the 2.0 architecture that evolved after that point. So after the reduction in latency from like 5 hours that they used to have to 20 odd minutes with Apex, they wanted to go even further. They were like, can we do 30 seconds and 20 seconds and so on and so forth? Then this model evolved. So in this model, they were consuming data from Kafka, and we directly now. So they were not writing it to the intermediate hop of S3. So we said, okay, we'll plug in our Malhar based Kafka input operators and read data from your data centers directly from the Kafka clusters you have there. And then they also introduced an enrichment operator, which would do a lookup from a file as well as a database uh, to basically see if they were able to for some metadata and reference values. Now, this Kafka input operator is available out of the box with Malhar, and it supports idempotency, exactly one semantics, and dynamic scaling. They had to write no specific code to include this operator. Just import it, and you're good to go. Then, besides that, they chose to keep the S3 pipeline on. So now, in this case, you're reading streaming data from Kafka from your co-located data centers, and you're reading essentially file-based batch data from S3 in AWS, and then you are actually merging that data at the dimension store level. So there would be aggregates coming from this pipeline and this pipeline that be combined at the dimension store level to give your end user a unified view of aggregations. Gonna take some questions. Yeah, so Ashish, the way we dealt with corrupt files was we 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 initiated a retry mechanism. So the corruption that we saw with files was around the eventual consistency of S3. So we would try to read the file. If the operator went down, we would put it in a list of blacklisted files. Try to read it again if it was consistent again. If it wasn't, then we would blacklist the file. There is not much you can do with Avro container files if they are corrupted in schema terms. So yeah. Okay, I'm gonna move on. No further questions. The challenges that we saw with this particular approach of one leg being truly streaming and the other being inherently batch was the DAG became a little more complicated. The Kafka operator, we were using dynamic partitioning, and with 0.82 based Kafka APIs, we were seeing a few challenges there. Uh, Offset maintenance became critical with dynamic partitioning, and over a period of time, that offset maintenance support was added to the Kafka operators, and it became very seamless. So the operator in Malhar that you see today is extremely robust and fault tolerant, and takes care of offset maintenance and dynamic scaling for you in a stateful way. At that point, it was a little different. Kafka 0.9 with its new APIs is also giving you very elegant semantics to keep a track of offsets, and the input operator with Malhar uses them, so it's good to go. We noticed that memory requirement for the store was growing as we were crunching in more and more data, which is sort of expected, but uh, unifiers, we had a large number of unifiers as a consequence, because the DAG footprint increased, and now you have to unify that data into a specific partition of the store. So a certain set of aggregates used to always go to a certain set of partitions of the store, because you want to reaggregate, and it just makes sense to have that key already present in that partition of the store for reaggregation. For example, you have a key K1 and value 100 associated with it, then if you see key K1 again coming in from your input operators, it would be routed to the same partition of the store, so that you can do an additive operation, and add your most recent value to the 200, which was the value that you had against that key in the first place. We noticed that more and more data was being transferred within the clusters because we were pulling from all of these clusters in a streaming fashion. So we introduced a notion of rate limiting for Kafka to make sure that we're not overly loading downstream operators. So the Kafka operators are very highly scalable, and some of the downstream operators, for example, a decompression operator is hits into bottlenecks with the decompression libraries you're using. In this case, they were using a zlib-based decompression library, so it was hitting bottlenecks while decompressing zlib data, while the Kafka operator could push 20, 30,000 events per second easily. Decompressor would not take more than 4 or 5,000. This is not a Apex level limitation. This is just an application code thing. Okay. Then from that point on, we evolved to a truly streaming architecture. We did away with the S3 level S3 reads. So now you have both the pipelines for your auction logs and your client logs reading from Kafka topics, and then doing some ETL decompression and flattening your ETL operator. This was an operator that was written by the team working on it, from the customer, because this operator has your business logic in it. Typically, while developing an Apex application, you are expected to write such operators which just tell you what your business logic should be and nothing else. Then the filter operator would just drop some fields and filter based on some enhancement criteria. Dimension aggregator would aggregate the filtered events and write it to a store, and then you have the same flow of middleware querying into a pub/sub based Kafka for getting those aggregate results. Okay, I'm going to move on. This is how the operational architecture actually looked like. So up top, you have the Apex application reading data from Kafka, parsing, filtering, aggregating, and writing to an in-memory store. Then you have a Kafka-based pub/sub to read and to basically exchange queries with the in-memory data store. And the UI, from the UI, you can visualize that. Down at the bottom, you would have typically the operational layers for running a production system, to truly enterprise-grade production system. So there was a monitoring utility for monitoring the Apex application that used to interact with the DT gateway, which in turn which in turn can set operator properties on the fly by interacting with the STRAM, or get some operational metrics from STRAM along, how many events are processed by Kafka operator per second, or how well is the parser doing on CPU, memory, how many events it's crunching, or how is the aggregator doing. All of those operational metrics can be queried using a REST API, and the DT gateway basically facilitates that conversation with the STRAM and returns those back to the monitoring utility. Based on this, they were basically populating some CloudWatch alerts. For example, if 4 of my containers go down in a frame of 5 minutes, then I want an alert so that the DevOps team can be notified. This made this made a lot of operational sense, because then the DevOps guys did not have to keep on watching the application. They would just get an alert saying, oh, 3 of my containers went down for whatever reason, and you need to take either corrective action or some preventive action. All of this was facilitated by using the DT gateway, which is a REST proxy to talk to your streaming application master. Okay, next slide. Here's how the application looked like at the end of it. There were 64 Kafka operators reading from 6 geographically distributed data centers. So there were 6 Kafka clusters sitting in 6 data centers, and these 64 input operators were reading from them. Each Kafka cluster had, I think, 7 brokers and multiple topics with multiple partitions, and we were providing a unified view into Apex using the Kafka input operator that is already available. The end-to-end latency came down from 5 hours to 40 seconds. This is the latency from ad serving to data visualization on the UI. For example, if I go to a page, I see an ad right now, then the company was able to capture that event within 40 seconds, capture and provide insights on that event within 40 seconds. So this is going through all the hops across the globe and coming to the visualization stage. There were 32 instances of this in-memory data store and 64 instances of the aggregator, and the peak memory footprint when data was at full throttle, 400,000 events per second, was 1.2 terabytes. Because they were using dynamic scaling, it would go up and down, but this was the peak. The in-memory data store was later replaced by HDHT, which is a Hadoop distributed hash table. Basically, the in-memory data store would spill over to a Hadoop-backed data store once the memory gets full. So HDHT gives you better fault tolerance semantics. So basically, can be better for recovery. Here are the learnings that we saw from that entire exercise. For DAG, for running a distributed application, DAG sizing is critical. You have to take care of the locality of operators and how you want to partition them. Benchmarking is usually required to do all of these. I'll give you an example here. Locality of two operators, right? So, for example, Kafka input operator with the decompress operator or the ETL operator. Now, these two operators can be container local because Kafka input operator is typically IO bound, whereas the decompressor is typically CPU bound. So ideally, you could put them into one container and save a little bit on the memory there. Now, in terms of locality, Apex offers you 4 modes of locality. You could have two operators that are node local, which basically means they are residing on the same node. They could be rack local, which basically means that they are on the same rack. The advantage of having a node local operator is like, let's say an upstream operator and downstream operator are node local, then you don't have to send any data over the network interface card between operator 1 and 2. Now there is container local, which basically prevents any serialization, deserialization of objects between two operators. In this case, in case of container local, two operators would be run within the same JVM, so there is no SERDE here. And there is a thread local, which is unique to Apex, really. And in thread local mode, two operators are essentially just logical functions called from the same function stack. So they're very fast. Same thread, just calling in functions. Nothing really happening in terms of data exchange between the two operators. Okay, I'm going to move on to the next slide. Besides locality, there is locality can be like co-locality or affinity. Affinity basically means that how you want two operators to be located. For example, I don't want two compute-heavy operators to be running on the same node. In this case, I would say, okay, you have anti-affinity, so you have to run on the other nodes. So Apex has support for both affinity as well as anti-affinity. Basically, you can tell an operator to not be co-located or be co-located. Memory sizing for heavyweight memory operators is critical. So typically operators that are going to store a lot of in-memory data or state, you have to size how many events or what size of events you would see over a period of time, and what would the flush of that operator be. Otherwise, you will run out of memory, and while Apex spills over to the disk, if you run out of memory, it's not a model you want to work on for long-running systems. Cardinality estimation for incoming data is critical. Again, this ties back to memory sizing. You have to know what are the different combinations in terms of your aggregations you would see. The upper bound on it you would see when you're running a long-running application. We've noticed that upstream operators typically tend to require more memory than downstream operators, because if downstream operators fail, then you build a bit of a back pressure on the upstream operators. Now, Apex handles back pressure in a unique way. It has a notion of a buffer server, which is a in-memory, which is, think of it as an in-memory publisher subscriber Kafka. So basically, the upstream operator would publish some data to a particular topic into this in-memory buffer server, and then the downstream operator would subscribe to that topic and read data from that topic. This is used for fault tolerance semantics and data replay. Buffer server state is only purged when a window is committed across all operators. That means that a tuple is seen, each and every operator has been successfully processed, and then the committed callback comes for that operator, and at that point only buffer server state is purged. Till that time, events would actually be residing in that particular topic for the buffer server. It resides in the upstream operator's memory, so it sits on the output operator of the upstream operator, and the downstream operator basically connects to it and consumes data from it. For end-to-end exactly one semantics, it's critical to understand that the semantics of the external systems rather. For example, Kafka, if you deal with a notion of where it has a notion of offsets, you can do end-to-end exactly once very elegantly. You can keep a track of the offsets and make sure that you're not reading data that you have already read. For something like a server listening on a port, someone is hitting REST calls to that port and you're listening on it, it becomes a little more intricate, because then you have to keep a state of what you have read, because you don't want to send the same event over and over again. Same is true for, let's say, you're sending alerts to SMTP servers. You have to keep a track of what you have sent. If the operator goes down, then you don't want to resend that. There is an interface that is available to do semantics like those, which is called a window data manager. So you can basically use that and snapshot the state of what you are doing in a window to a persistent storage. There is a default implementation available out of the box, which is the FS data manager, file system backed data manager, to do that. And I would say think fault tolerance and data recovery before you start implementing any distributed system. Let's take a look at how the system was before we started off with Apex, and how Apex really reduced the time to get insights. So the previous versions were like 5 hours plus latency. Then with the batch based reads from S3 with Apex, it came out to 20 minutes. And then with Apex again, with streaming real time reads from Kafka, it came down to 30 seconds. Here's the list of the operators that we used to do that. I'm doing a quick time check and sort of rushing through now. Apologies. Feel free to ask questions right now. There was a S3 file reader which did recursive reads from S3 based on a certain pattern. You could include and exclude records and even go back into some S3 folders. There was fault tolerance semantics and replay built into the operator. This basically leverages the abstract file input operator from Malhar. So a lot of it is available out of the box from Malhar. Kafka input operator, again, coming from Malhar. Pojo enrichment operator coming from Malhar. The Kafka operator could read from multiple Kafka clusters, did offset management for you, and supported fault tolerant reads. The Pojo operator the Pojo enrichment operator had a notion of a primary and a secondary store to do lookups from external systems. So there was a primary cache in which your more frequent data would be, and it made a query to the external store only if it required to. So this is a configuration driven operator. You just had to give it a Pojo and which fields to look up for in the Pojo. So it would take those keys, query the store, either the primary cache or an external store, and then give you the values associated with it. And you could do your filtering or purging or whatever you needed to do with it. Okay. Moving on, then there was a JSON parser, again, a Pojo based operator. You just had to give it it takes a Pojo as an input, give it a schema for the Pojo, and it takes a JSON tuple as an input, give it a JSON schema, and it would create a Pojo for you and output it. So you don't have to do much processing with it. The dimension store was an in-memory hash table, essentially. It supported reaggregation of events. They were partitioned per view. So let's say a publisher is a view, an advertiser is a view, and a demand partner is a view. So data was being partitioned into the store per view, and aggregations would be at a lower level than this view. And there was a low latency publisher subscriber based model Kafka support built into it for answering queries. Later, this was moved to HDHT, which is the same dimension store but backed by persistent storage. So even if you kill an application, you stop it, you do a cold restart, you would have those aggregate values persisted to the store, and you can query them back. Here are a few concepts around the dimensional model. So matrices are basically pieces of information around which you want to collect statistics about, basically measures of entities. Dimensions are those entities which you are measuring, basically variables which can impact your measures. Combination is a subset of a dimension. They are basically sets of dimensions for which one or more metric would be aggregated. And aggregations are the functions that you want to apply on to capture that information or that statistic. Here's an example. In this particular ad tech use case, you would have dimensions as your campaign ID, advertiser ID, and time. And your matrices would typically be your cost, revenue, click, something measurable is a matrice. And your aggregate function would be, I want a sum of my revenue, or I want a sum of my clicks, or I want a mean of my revenue or cost, etc. And then your campaign combinations would typically be like campaign ID versus time, or advertiser, or a campaign cross advertiser cross time. So you want to see how your campaigns are doing for a given advertiser in a given range of time. This is how it would look like. How would you set this on your schema? Pretty straightforward. You have a dimensions compute operator, and it takes in a JSON schema. So you don't have to write any complicated aggregations yourself. All you would do is create this schema and pass it as a string parameter to that dimensions compute operator. This schema has dimensions which are represented by keys here. So the key name here is campaign ID, and it has a data type associated. You typically associate a time-based notion to any aggregations. So you have time buckets associated. Here I'm bucketing it into an hourly time bucket or a daily time bucket. So 1 day and 1 hour. Then you would have your values or matrices, right? Metrics. Here impressions, clicks, and revenue are my metrics. And I want to apply aggregator function on them, which is sum in this case. After that, you would have combination of those dimensions. So I'm saying, okay, I want a campaign ID with ad ID for both these time buckets. So 1 day and 1 hour, I'm doing campaign ID and ad ID. And then the next one is creative and campaign, and I want to do it at 1 day and 1 hour levels again. And then there is publisher, ad, campaign, and I want an additional metric besides the one I have here, which are impression, revenue, and click. I want an additional metric of revenue too. So this is how my dimensional model would look like. Some of the other use cases are real-time monitoring, learning, and allocation engine, basically providing some feedback in real time to while you're serving ads, so you can optimize your auctions. Here's how a DAG builder would look like. So you have an input you have a palette of operators here, and you can specify schema on your input-output ports for handling POJO or passing a tuple and setting a value on the POJO. You have an input operator, then a parser, then an enricher, a dimensions compute operator that sends results to a store. This is an offering out of the RTS platform that lets you assemble pipelines using a DAG builder interface. Here's a logical view of, let's say, a file splitter, how it would look like. So you're reading data from files, emitting some metadata to a block reader, and then file metadata to a tracker to keep a track of which files you've read. And then the block reader would read the actual data, send it to a block synchronizer, and then you would merge all those blocks into the files. This is how the application will actually look like. So you have 4 instances of the block reader. The block reader is reading some block data and writing it to a writer. The writer is writing that data into individual blocks, and the synchronizer is basically synchronizing them. So you have a unified view at the end. Here's an example of an in-stream visualization. So here's your impression, clicks, and cost, an average of that in real time using widgets available out of the DT console. This is, again, RTS offering. Any more Q&As? Happy to answer. If not, we can call it a day. Guys, have a great weekend. I'm going to wait for a few seconds. All right, no further questions. Great to have you guys. Have a great weekend. Thank you.